Okay, so I will consider manifolds associated to tree. With vertices I, so set of vertices V labeled by integers. Let's see. It can look something like this. And so what does this mean? What is it? How do I construct C manifold? So if I have a kind of a dot vertex labeled by integer p, so this I can understand this as a S1 bundle over S2 with the first chain class given by this integer p. And then if I have a vertex with kind of let's say m outgoing edges, this means I have to remove these m fibers, and this creates m C2 boundaries, right? Because the kind of the name. If you remove a point on the base, this kind of removes the fibers one, and the this creates a torus boundary. Because tubular neighborhood of I can also understand the kind of removing a kind of small neighborhood of a point at the base. So this creates this. If I remove S1 from the manifold, this creates a torus boundary. And then if I have kind of when I have an edge connecting two vertices, this means I glue to the two T2s which created by this in this bundle by S transformation in the mapping class group of the torus. Essentially exchange the fiber circle with the small circle on the base.
And then in some picture, just like in some picture with two dots and one line that corresponds to S3, leave it out of 2 for which is it?
Sorry, this something like this? What is
it? Is number. Well, maybe it's the right number. So you know, they make a 3-sphere.
Okay.
And you glue it together out of 2 solid forms.
Yes. Well, so but solid well, I'm sure this gives you 3 sphere. Yeah, this is 3 sphere.
And for band space,
you have LPQ. I can consider a continuous fraction decomposition of this. And I put these numbers here in the line. You can also understand for people more like algebraic geometers, one can think about this graph as a resolution graph of a singularity, and then the manifold is a link of the singularity.
And in particular, L1 from Q is probably the one.
Well, I don't know. You actually can do just a single. It's a single dot. I mean, you can also do it like this. Because yeah, there can be different graphs which give the same manifold, and they are related by what is called Newman moves. Yeah, you can do LP1, for example, like this, or like this. And for in terms of singularity series, you just blow up at one point. Okay, and basically, yeah. So my goal is to write explicitly to be able to do this count, find this coefficient explicitly for all manifolds of this form. That's a punchline. So yeah, we essentially give an algorithm to, like, I mean, algorithm which you can plug. I mean, you plug. I mean, I have a program in a computer which essentially gives you calculation of those coefficients. Yes, that's it. Well, yeah, kind of, but they were not motivated enough for some reason. They said they can do this, but it's not it's not worse. I don't know. Anyway, I shouldn't name the names because it's recorded. Okay. So yes, sorry, and okay, so we can consider B is a adjacency matrix of this graph, and to which we add these Fi's and numbers on diagonal. Right, so it's a matrix, quadratic square matrix of the size being the number of the vertices, and then I want, if I consider the inverse of this matrix, which exists whenever this manifold is a rational homogeneous sphere, which I'm still assuming, you can consider kind of a block of this matrix, which I will denote by C, which corresponds to a certain subspace. Like, okay, we should have defined it earlier. So H is a subspace of vertices, subset of vertices of degree greater than or equal than 3 inside V. So for example, in this graph, this is this point and that point. And then another kind of useful data which I can extract from my graph is the following. So I also consider L to be a kind of vertices of low degree, namely of degree 1 inside V. So in particular, so for example, if I draw a graph like this, so these two vertices will be in H, and this will be in L. And for each vertex, since I'm assuming this graph is a tree, for each, if I have a vertex in L, I can uniquely associate to it some high valency vertex, H, which is the closest high valency vertex to H of A. A degree of vertex, it's a number of edges which connects. Yeah, just one. So for example, here the degree is 4. These are not important. And then, so similarly, actually, as I mentioned for the length space, I can. So for this kind of, I have a linear part of the graph which connects this low degree vertex, like vertex of degree 1 with high valency vertex, by some sort of linear piece, and I can consider the corresponding continuous fraction to this kind of corresponding to this leg, and this will be some rational number corresponding to this A here. So these integers, and for me this number will be important. Actually, yeah, this fraction is an invariant of this part, so you can do some sort of change. You can do changes on this kind of linear part, but which will be result in homeomorphic manifolds. So the only this local.
anything you want. Thing in terms of these similar.
You're just writing. I hope to be
Yes. Yeah. It's kind of invariant data. This rational number. You can understand this part as this kind of part as S T F1 S T F2 together. I mean, this whole piece as gluing of two torus, just not executing. So this was you just use S, but more generally you can associate this part as gluing with this. No, not of course not. Yeah. It would be too ambitious. Well, I mean, this is a kind of, you can also understand it in terms of some sort of surgery on some sort of link, and here it's a link of basically unknots. And but for more general manifolds, you need more complicated links. Okay, and the point is that I want to write explicit in terms of this data. I want to write explicit formula for B of psi. It's true, yes. Yeah, it's. I mean, it's a very large class, but it's quite limited. Yes. So it will be an integral over some finite dimensional integral. It's over 1/2 dimensional cycle, compact cycle in some in a quadric hypersurface. This will be a hypersurface in affine space Cn, given by this equation. C, as you recall, this was a part of this part of the adjacency matrix. And okay, so what I integrate over, so there will be measure to convert the kind of sum. Or you can, yes, independently understand this kind of measure part. So B was adjacency matrix where on the diagonal, on diagonal you add these integers, and here you have 1 or 0 depending whether there is an edge or not between two vertices on the off diagonal part. Then you invert this and you take this block which corresponds to kind of rows and columns they elaborated by vertices, and then you just take a block in this inverse matrix which corresponds to vertices of degree at least 3. This actually this measure is a standard measure of integration over sphere, if you wish, but I can write it explicitly. So you sum over permutations, and so if I understand my set of high valence vertices H1, H2, and dot dot dot, then this would be the permutation sigma 1 of H1, D U sigma 2 of H2, dot dot dot, D U sigma H. So this is the number of high valence vertex of H. This part has not the measure. Yeah, the measure, and this doesn't have. What is next going to have Xi dependence? This part doesn't have Xi dependence yet. It actually was. This it was made. It was designed so you remove Xi dependence from measure in this space, and so Xi will appear here. So you have now you have the following function. In the numerator, you have a product of vertices of degree 1, sine psi, In the previous work, we can use we consider just Seifert manifolds, and for that you can use the formula by Rosansky, and also there is a version by Marcus Marini for Seifert manifolds, which correspond to this type of Seifert manifolds correspond to these graphs. And there in that case, actually just B0 psi is you have expression for B0 psi, you don't need integration. And in sense, this is a generalization of that formula for general plan names. And but first of all, if it has loops, then it's automatically not a rational homogeneous sphere. This H1 is not going to be finite. It's one of the reasons. Oh, you see, yeah, this is a pretty complicated formula, but in any case, this is just boils down to the kind of problem. So analyzing the monodromies of this function is just a question of complex analysis in multiple variables, which you can do. This is yeah. And, so let me. So in particular, like where these singularities. So very roughly speaking, the singularities of the B0 psi can come from well, singularities of this in the denominator. But to be precise, this is a kind of, it's not just like if it's just a singularity, of course you can shift kind of shift a little bit your contour, so the contour doesn't pass through the singularity. The singularities which actually appear roughly is like if the singular loci they kind of pinch down the integration contour. That's where the singularities can appear, and you can use this perspective to analyze this singularities of this function. And so in particular, you can make the following statement. So singularities can be grouped according to subsets of the set of vertices of degree at least 3. And in each group, they are classified by tuples of non-zero integers. So for each high valency vertex in this subset, we have a non-zero integers, but you also have to a quotient over equivalence relation, which changes overall signs. And you also have additional conditions that such that for any element of this subset of high valency vertices, there do not exist this number of distinct elements in the set of vertices of degree 1, such that so for such that this so this high valency vertex is associated to this to the vertex of degree 1 in this way as we discussed before, and this PA number, which was numerator in this continuous fraction, divides this integer number. Anyway, this is some technical condition, which basically means that this the naive singularities, they are not cancelled by the numerator. Okay, and the other b's will come out as monodromies of this B0. and which are yeah, and then you can the other b zeros you can actually write down. So by you can write like roughly speaking, by taking some sort of residues here, you get other b's. Yeah. Anyway, well, other b's, they come as monodromies as b's. So let me make a now even more specific example. Yeah.
You rephrase it as instead of beginning at the beginning of your talk, you wrote down some finite dimensional integrals and analyze stuff like that. And basically reminding us that the thing called conventional theory can use analyze.
Yes.
And the conventional theory tells you that the integral there's some relationship to the monodromy. But an Agnew's question was, if you apply this method from the beginning to this integral, then you should learn that somehow the coefficient monodromy of this integral are intersections of the symbols of this integral.
Well, this is not an exponential integral here. I'm not sure. This is already b.
But,
yeah, I mean, I want to apply this to this b. What I just I want to calculate monodromies of this b.
yeah, but
The product here doesn't only go with W could be a logarithm.
No, but
adding an integral of x exponential integral.
no. There we have a. I mean, we have a no, for Petrov-Lepsch theory, we have to consider particular case of this, right? Well, more generally, we can consider the important part is the dependence on this k is only here. Anyway, you can write. Yeah, the point is like, how do you obtain this? You obtain this by writing some sort of partition function Chern-Simons here as some sort of as an integral over, like, okay, actually one more variable, but which looks like this, some of this form. Okay, some finite dimensional integral. You first write it in this way. Yes. Yes, finite dimensional integral, and then you from this you get b0. Yes.
Why don't you analyze them?
You can do this. Yes. Okay. But well, but here, yeah. So, but I mean, here it's not so trivial because this R is not holomorphic. So actually, it's not enough to analyze symbols of this. You have to analyze all the. You still have contribution from singularities of this. So it's not. Yeah, it's not completely clear. How to write? I don't know how to write. Yeah, explicit like formal finite dimensional integral, where this is holomorphic. This I don't know. Kind of, yeah. The point is like if you in general you can kind of reduce some sort of if you start with something like this, you might be able to reduce this to some sort of low dimensional integral. And actually can study this type of phenomena in like low dimensional case. You can just kind of reduce the number of integrals like m less than n, but you by the cost of earning some sort of rational function here with singularities. You kind of this is a partial kind of reduction, which you do in this graph. Anyway, okay, let me consider now even more specific case. This graph. And yeah, and then I will consider this example, and then I stop. -1, -2. So here there is this the set. So let me of high valence vertex is just this. Yes, you can think about this, or you can think about this. This is more or less equivalent. Yes. You can think about yes. It might. You can do this. I don't say this is yeah. It's a,
Why do you prefer this large expression?
because it's a more universal answer, right? Well, the way I presented it is the question was in finding B0.
Okay. It's more explicit answer.
Yes, yes. It's more it's easier. Honest answer, it's easier to formulate the result this way. Yeah, I could write it in this way, but it would be a bit okay. But again, it's still you do this finding, but it's still it's not the usual perturbation because you have singularities. Let me emphasize it.
Do you know how single integration cycle that corresponds to different class actions? The form R.
Different. Yes. Yeah.
That doesn't show the integration cycle.
So basically, yeah, the critical points of Chern-Simons, they come from critical points here and singularities of this function. If I just consider critical points here, of course, I'm not going to get correct thing. So yeah, so here in this particular example, so H is the set of high-valence vertex is a set of two elements which are labeled by just 1 and 2, and so this example of integer homology sphere, so H1 is 0. So what is this singularity structure in this case? So the promised, sorry, it's announced you can group singularities according to the subsets. And and here, so I will make a table of some sort of flat connections. And so okay, first of all, you can consider empty subset, and this corresponds just to trivial flat connections with 0 Chern-Simons functional. Then consider subset which is just take 1, and this will contain. Well, I tried to find an easy example, but so it will contain the 40 different flat connections, connecting upon flat connections with the following. Yeah, I'm not going to write everything, of course, with the values of Chern-Simons function looking like this, and then will be a group corresponding to this subset, and here there will be 12 connected components of flat connections with Chern-Simons functional 79. And finally, there will be a subset, which is a full set. By the way, this also gives you kind of a prediction about a classification of moduli space of flat connection. Actually, the representation, yeah, this character variety for this manifold is actually not known in the math literature. So it also gives you prediction for the. And this group, there will be 10 components. And then, for example, I can consider a series corresponding to a like pair of trivial flat connection and the flat connection with this value of Chern-Simons functional. So it's from this group.
Yeah, the statement is you're extracting the bizarre fractions from your formula.
Yes. It's the positions of the singularities of that. And what I'm writing now, I extract from the more like not just positions, but the structure of singularities. And the other way around, I get 0, and then, for example, I can consider from flat connection from this group to some flat connection in this group. Yes, up to overall simple overall shift. Oh, sorry, this is actually, yeah, this overall shift I was wrong. Like, let me not. There's basically some simple rational number. Oh, sorry, sorry. What I wrote it, I mixed up this two. Sorry, this Q13. Well, anyways, it might be not so important, but okay. And so what about, for example, what I did write is flows directly from kind of this trivial to this. You can ask a question, for example, about something like this. And here there is a subtlety appears that this is actually in principle, so this is ambiguously defined in the sense that this has wall crossing type of phenomena. So why does this happen? So in this, if I consider in this psi plane, so I will have these singularities corresponding to values of Chern-Simons functional 24, 55 plus integers. And then, and here was my trivial flat connection. And the point is that in between, I will have flat connections from group 1 and 2. And then on trivial flows from this trivial to this one. So if I try to directly flow from this to this, I encounter in between these other critical points, and I have to do some perturbation. And the way you do a perturbation, the answer will change. So, and there are two natural ways to do a perturbation here. Of course, there are various ways to do, but so first is gives me chamber 1. Is that the way I do perturbation is that, okay, I keep my critical points corresponding to the subset, to the group corresponding to subset 1, 2 intact, but I shift a little bit critical points corresponding to group 1 above, and critical points corresponding to group 2 below. Or in the other chamber, I can shift them all in the same direction. And so in a sense, this is a kind of usual wall crossing phenomena in kind of Landau-Ginzburg model, if you wish. We have infinite dimensional Landau-Ginzburg. So in this chamber, the result for 24 for this count is the following. And this chamber, the result is actually quite different. You see the powers which appears are much more sparse. Yeah, and those two are related by so the difference between two results, they are one can check that they are related by kind of the usual wall crossing formula. So it's sum over. So suppose we yeah, so we move these singularities above this line, and when they cross this line, the wall crossing happens, and what you do is the sum over I0 alpha, I alpha 24. You have this kind of intermediate flows where alpha belongs in group 2. I think it's yeah. Well, it's a general fact about Picard-Lefschetz theory. Yes. So I think yeah. Yes. I mean, if you use this formula, this is automatic. I mean, the wall crossing formula. Of course, like yeah. If you use this finite dimensional integral, yeah, the wall crossing formula should be automatic. Yeah, it just happens that because yeah, if you yeah, it just being like this we have this yeah, the critical sense they are on the same line, the critical values lie on the same line. I mean, there's no actually it doesn't like since there's no flows between there's actually no flows between group and 1 and 2, so the relative position doesn't matter because there's no flows between these two groups. But since there are flows between kind of there's a more general phenomenon. They have kind of hierarchy of the flows. So you kind of can flow from this to this to this, and you can flow from this to this. But for example, there is no flow like this, and there also no reverse flow. Okay, that's all I wanted to say.